So here we have this beautiful equation of the circle, which is x squared plus y squared equals to r squared. But since this is Desmos, it is much better if we set up our own kind of radius. So for a guy like me, I'm just very simplistic. Instead, I'm going to set up my radius as square root of 2 over 2. Alright, so this is our circle. Perfectly round and absolutely adorable. But you want to be naughty, so you decided to pancake your circle. And it's no longer a circle. So I can go ahead and put random values beside the x and y. So what if I did this? And at that point, it shrinked. It turned into a line. At this point, it looks like a line, but when you zoom further, there is still area underneath this area of this ellipse. You wouldn't even consider that this is an ellipse anymore because it's so flat. You can barely see its true shape unless you zoom it. So how do we get the area of this? Well, the process is actually very simple. Artists are definitely going to kill me for using this specific platform for mathematics, but I don't care. So moving on, so we have the standard equation for x squared plus y squared is equals to r squared. So as we all know, this is the standard equation of a circle, but we can go ahead and write its coefficients. So we have we can go ahead and write this way: a x squared plus b y squared is equals to r squared. Now you might be asking, why is there a coefficient beside x squared and y squared? I thought that is y minus k squared or x minus h squared. Well, you'll see why. So for this equation to become a circle, obviously we need to assume that a is equals to b. So no matter the value, like a is equals to 1, 2, 3, 4, 5, 6, 7, it's got to be equal for b as well. But here in this case, like during the last clip, as I've shown you, in this case, I want to assume, I want to set up that a is not equals to b. So even if I put any random values, they shouldn't be equal in this case. So are they still a circle? Obviously not. Obviously fucking not. So what are we gonna do? So to reveal its true shape, we're gonna go ahead and divide both sides of the equation by r squared. So we can go ahead and do that. So we have a x squared plus b y squared is equals to 1 r squared. But we can go ahead and write this as x squared all over r squared all over a plus y squared all over r squared all over b. So we have, so look at this. Here and here, this is important because as you can see now, if we equate this to 1, this looks very familiar. So if you know your conic sections very well, this is the standard equation for the ellipse. So we have x squared, a squared plus y squared all over b squared is equals to 1. So that is our standard equation for the ellipse. So this is what we're going to focus here. So our a squared, we represented a squared as r squared, okay, my writing is bad, r squared all over a. And then we represented b squared with r squared all over b. Alright, so why is this very important? Because if we take the square root of both sides, watch this. So if we take the square root of both sides, we can go ahead and say that a is equals to r all over square root of a. And then that b is equals to r all over square root of b. Alright, so what do we do from here now? So once we have represented a and b as this, let's go to the formula for the area of the ellipse. So we know that the formula for the area of the ellipse is simply equals to pi a times b. Alright, so let's go ahead and substitute it. So remember, our a is r all over square root of a, and our b is r all over square root of b. So let's go ahead and substitute that. So we have pi multiplied by r all over square roots of a multiplied by r all over square root of b. Now let's combine. So let's go over here in these numerators. I suck at drawing arrows. Please stick with me here. So in our numerator, r times r is r squared. And what's square root of a times square root of b? Well, let's look back at the laws of radicals. So if we deal with a situation where square root of a is multiplied by the square root of b, that's also equals to the square roots of ab. So if that is the case, we can now go ahead and combine this. So now we have pi is multiplied by r squared all over square root of ab. Fuck. sorry for the word. So here we can also simplify this further by moving the constant here, pi, all the way to the numerator. So that's now finally our final formula for the area of our ellipse, that is from our silly little circle equation that we somehow pancaked, is pi r squared all over the square root of ab. And that is our formula. So looking back to our silly little pancake, what if we try to plug in the values? So now we're back here, and according to our formula, we're going to go ahead and use it. So substitution. So we have pi multiplied, what's our radius? So it's the square of square root of 2 all over 2. So we can just go ahead and type square root of 2 all over 2, and then squared. And then finally our a and b sit, and here, even though there's nothing beside x, that's automatically times 1. So we can go ahead and say 1 times this absurd number we have here. So we have 95,235. Now look at this. 0.0050900445558. So it tells us here that the values of a and b from the circle equation is inversely proportional to its area. Because as you completely flatten this thing, if you isolate one variable, which is a or b, and then you increase the other, the area shrinks as that specific variable is increased continuously. And I think that's pretty cool. Well, that's a pretty cool Easter egg or something that we should review back in mathematics. So yeah, that's all for today's video.